You're right, you're very close. I mean, you're on the right track. Oh, we have not done the power series expansions yet. That's the next chapter. Tomorrow. Power series come tomorrow. So with today's whatever we have done until today, e to the power x cos y plus I e to the power x sin y. Suppose I put x equal to 0. It is simply cos y plus I sin y, correct? And then when y equal to 0, 2 pi, 4 pi, 6 pi, 8 pi, what exactly is happening? You keep getting the same value, correct? You keep getting the same value, right? So the question now we can now ask is, suppose if this function f, suppose this function fz were a rational function, let us say pz by qz. That means that this rational function is taking the same value at infinitely many points, right? So it takes the value a, take the value 1. Where does this function e to the power x cos y plus I e to the power x sin y take the value 1? It takes the value 1 at 0 and 2 pi I, x is 0 and y is 2 pi, isn't it? It takes the value, your function f of z takes the value 1 at 0, 2 pi I, 4 pi I, 6 pi I, 8 pi I. So if this f of z were a rational function, say pz by qz, that means that pz by qz will be 1 at infinitely many values of z, right? So pz will be equal to qz for infinitely many values of z. Pz minus qz is a polynomial. Can a polynomial vanish at infinitely many points? It cannot, unless it is the 0 polynomial. So now we are seeing that f of z must be 1 for all values of z. This is a contradiction. So this function e to the power x cos y plus I e to the power x sin y is not a rational function. Is the argument clear? If it were a rational function pz by qz, then let us put z equal to 0, 2 pi I, 4 pi I, 6 pi I, etc. pz by qz is 1 for all these values, right? So pz equal to qz for all these values, right? Therefore pz minus qz, which is a polynomial, is 0 for infinitely many values of z. Therefore it must be the 0 polynomial. So pz must be identically the same as qz. So the ratio pz by qz is identically 1. So the function fz is a constant function, which is a contradiction. Yeah, they are both polynomials. Well, you have to prove now that a polynomial of degree n cannot have more than n roots. Yeah, now how do you prove that a polynomial of degree n doesn't have more than n roots? What is okay, take a polynomial of degree n. What is it? It's a naught plus a1z plus a2z square plus an z to the power n. Now, this is 0 for z equal to z1, z2, z3, z n plus 1, correct? So substitute these values, put z equal to z1, you get 0, put z equal to z2, you get 0, put z equal to z3, you get 0. You have a system of n plus 1 linear equations for a0, a1, a2, an. What is the determinant of the system of linear equations? What is the determinant first? The determinant is 1 1 1 1 1 z1 z2 z3 etc. zn plus 1 z1 squared z2 squared z3 squared zn plus 1 squared etc. z1 to the power n z2 to the power n zn plus 1 to the power n. What is this determinant? It is the van der Waals determinant. What is the value of the van der Waals determinant? Product of Zi minus Zj. We have studied this in the differential equations course when we compute the Wronskians, remember? But then what is our assumption? That these Z1, Z2, Zns are all pairwise distinct. So van der Waals determinant is not 0. You have a system of homogeneous linear equations whose determinant is not 0. So it has a unique solution, namely the 0 solution. So A0 is 0, A1 is 0, A2 is 0, An is 0. So the polynomial is the 0 polynomial. That is the argument. Correct? Is it okay? So if f of z is pz by qz, then f of z takes the value 1 at infinitely many values of z. So pz equal to qz for infinitely many values of z, or pz minus qz is 0 for infinitely many values of z. If we have a polynomial which is 0 for infinitely many values of z, means that that polynomial must be the 0 polynomial. So pz must be identically equal to qz. So pz by qz is 1. So f of z is 1. That is a contradiction. Right. Okay. Some exercises for you. Examine whether the Cauchy-Riemann equations hold in the following cases. F of z equal to cos x cos y plus I sin x sin y. Cos y is what? It is a hyperbolic cosine, e to the power y plus e to the power minus y by 2. And what is sin y? E to the power y minus e to the power minus y by 2. And the next problem is f of z equal to cos x cos y minus I sin x sin y. Third part is f of z equal to mod z squared. We already finished this problem. Mod z squared is x squared plus y squared. And the fourth problem is mod z squared z bar. If you look at these texts like Kreyszig or Churchill Brown or something, you will find lots of examples. I mean, I am just giving you a sampling. I mean, I could easily write down some 50-60 problems, but you just don't have time to copy down all of it. So I just picked up a sampling of these exercises from. They are all standard exercises. It will be available in almost all texts. So what we have just is a cross section of these exercises. The second part is, suppose f of x plus iy equal to u plus iv is complex differentiable on omega, and u and v have continuous second order partial derivatives. Continuous second order partial derivatives. Prove that del 2u by del x squared plus del 2u by del y squared equal to 0. It will come, don't worry. He's taking forever to adjust it. So write down. Which one have you written down? Shall I read out? Third part is f of z equal to mod z squared. The fourth part is f of z equal to mod z squared z bar. Second question, f of x plus iy equals u of xy plus iv of xy is complex differentiable over omega, and u comma v have continuous second order partial derivatives, prove that u and v are harmonic functions. Prove that u and v are harmonic functions. That is, u and v satisfy the Laplace's equation. That is, del 2u by del x squared plus del 2u by del y squared equal to 0, and del 2v by del x squared plus del 2v by del y squared equal to 0. Correct? So, what does the problem say? That if you take a function which is complex differentiable, then its real and imaginary parts are harmonic functions. The real and imaginary parts are harmonic functions. Okay. Now, the next question that I want to give you is the following. Suppose, write down, suppose f of x plus iy, suppose, okay, wonderful. Suppose f of x plus iy equal to u of xy plus iv of xy is complex differentiable on omega. Suppose f of x plus iy equal to u of xy plus iv of xy is complex differentiable on omega. Show that the loci x comma y such that u of xy equal to c1 and the loci v of xy equal to c2. The level curves of u and v. U and v are two functions of two variables, and the level curves of u and v cut each other orthogonally. That is, the two sets of curves are a pair of orthogonal trajectories. The two sets of curves, these two sets of curves are orthogonal trajectories. In other words, the level curves of u and v cut each other orthogonally, or they intersect orthogonally. And then the next question is, discuss the loci of exercise 3. Discuss the loci of exercise 3 in the case when f of z equal to z plus 1 over z. For the case f of z equal to z plus 1 over z, discuss this loci. This particular function z plus 1 over z is called the Zhukovsky's function. It plays an important role in the construction of the Zhukovsky's airfoils. So, discuss these loci for this particular function z plus 1 over z. Okay. Finished writing? Right? Shall we proceed? Very good. So, now we have seen that the real and imaginary parts of a complex differentiable function are harmonic functions. So, the next subtitle is harmonic functions and harmonic conjugates. Let us finish this off today, let us not keep it for tomorrow. It's a small section. Harmonic functions and harmonic conjugates. A function u of xy which has continuous second order partial derivatives is said to be harmonic if it satisfies the Laplace's equation. I just dictated all these things just a while ago. What is the Laplace's equation? Del 2u by del x squared plus del 2u by del y squared is 0. So, we have just seen that a function of two variables which has continuous second order partials is said to be harmonic if this equation is satisfied. Now, given such a u, given a harmonic function u, a function v is said to be a harmonic conjugate of u if the pair uv satisfies the Cauchy-Riemann equations. That is, if del u by del x equal to del v by del y and del u by del y equal to minus del v by del x. Is it clear? What is the harmonic conjugate of a harmonic function? Given a harmonic function u, a function v is said to be the harmonic conjugate of u if the pair uv satisfies the system of partial differential equations del u by del x equal to del v by del y, del u by del y equal to minus del v by del x, correct? All right. so that u plus iv is a analytic function. So, or complex differentiable function is a complex differentiable function. Analytic functions I will explain later on. At the moment it is the function u plus iv is a complex differentiable functions. What are analytic functions? Will come to it later on. We now prove the following theorem. Suppose omega is a star shaped domain. Remember, I began the lecture by telling you what is a star shaped domain. Suppose omega is a star shaped domain and you have a harmonic function u on a star shaped domain, then there exists a harmonic conjugate v. Right? This harmonic conjugate is unique except for an additive constant. Two harmonic conjugates will differ by a constant. The difference of two harmonic conjugates will be a constant. So, given a harmonic function u on a star shaped domain, there exists a v such that u plus iv is complex differentiable. Correct? How do you prove this? To prove this, let us recall from vector calculus the concept of irrotational and conservative fields. When is a vector field said to be irrotational? When the curl of the vector field is 0. Does it imply that if the curl of a vector field is 0, does it imply that the vector field derives from a scalar potential? If curl of f is 0, does it imply there exists a scalar field phi such that f is grad phi? No. What is the condition? The domain must be star shaped or simply connected. Simply connected is a concept that is difficult to describe. Let us stick to star shaped domains. You need some domain geometry. I explained this in the MA 108 course, and unfortunately I do not have time to go over the whole details all over again. This should have been done in the vector calculus course. That curl of f is 0 by itself is not sufficient for you to conclude that f is the gradient of a scalar field. You need a blank, you need an additional condition, you need an additional hypothesis on the domain. Some domain geometry should be available, and it is one such condition is that the domain should be star shaped. Correct? So, if it is a star shaped domain, remember that in the hypothesis of the theorem that I just stated, the domain was star shaped. In a star shaped domain, if a curl of a vector field is 0, then the vector field derives from a scalar potential. So, that is what the next slide says. If omega is a star shaped domain in R3 and if f is a vector field such that the curl of f is 0, then there exists a scalar field phi such that grad phi equal to f. Star shaped is a condition that is essential. You could drop star shaped and you could put something else like simply connected or whatever, but some domain geometry is required. Without domain geometry, this theorem is not true in general. So, now what do we have? In our case, we have a function u such that del 2u by del x squared plus del 2u by del y squared is 0. The function u does not depend upon z at all. Correct? Now, I can write this equation as curl of minus del u by del y I plus del u by del x j plus 0 k. You compute the curl of this is exactly going to be the case. So, here I cooked up for you a vector field minus del u by del y comma del u by del x comma 0 whose curl is 0. If its curl is 0, that means that there exists a V such that grad V equal to minus del U by del Y, del U by del X 0. That means that del V by del X is minus del U by del Y, del V by del Y is del U by del X. The Cauchy-Riemann equations are valid. So, conclusion, given a harmonic function U on a star shaped domain omega, there exists a harmonic conjugate which is unique up to additive constant. The exercise that two harmonic conjugates differ by constant is left as an exercise for you. Okay. All right, couple of remarks. If V is harmonic, if V is the harmonic conjugate of U, it is not true that U is the harmonic conjugate of V. The relationship is not a symmetric relationship. The correct statement is if V is the harmonic conjugate of U, then minus U is the harmonic conjugate of V. Remember this. Don't simply say that U and V are harmonic conjugates of each other. That statement is false. That's a false statement to say that U and V are harmonic conjugates of each other. I heard this statement from people and I am making this remark here. If V is the harmonic conjugate of U, then minus U is the harmonic conjugate of V. Look at the Cauchy-Riemann equations and you will see it. In one of them a minus sign appears. Correct? So please be careful. Just don't loosely say that U and V are harmonic conjugates of each other. That's a wrong statement. Okay? Some exercises for you. Let us just finish these exercises and then call it off. Show that the function half log x squared plus y squared is harmonic and find a harmonic conjugate in the right half plane z belongs to C such that real part of z is bigger than 0. Is there a harmonic conjugate on C minus 0? Is there a harmonic conjugate on C minus 0? Just write this down. There are some more exercises. Here, show that this problem relates to calculus of several variables, multivariable calculus, and this property spelt out in exercise 3 is called conformality. This is called conformality. When I said conformal mapping, this is what I mean. The angle preserving property of these functions. This problem is from Nehari's book. This exercise is from Zeev Nehari's book. The title of the book is Conformal Mappings. The second exercise is from the book of Zeev Nehari, Conformal Mappings. It's a very interesting problem. It's an easy problem. It's just interesting problem. So, all right. One last exercise, exercise 4, which is important, and we shall use this exercise later. So, if U plus IV is complex differentiable on a domain omega, show that capital U equal to half log U squared plus V squared is harmonic on omega. Yeah, so there is a correction in this definition. A function f from omega to C is said to be analytic if f is complex differentiable on omega and U equal to real part of f and V equal to imaginary part of f have continuous partial derivatives. We will return to this definition of analyticity in a subsequent lecture. And with this definition, I conclude the second lecture. And we will return to the power series, etc., in the third lecture. Thank you.